Here we have a parallel plate capacitor, and up here is the negative plate, and down here is the positive plate, and then we have a charge in between them. Now the electric field between these two plates is uniform, and I guess I can calculate it if I need to. It's 12 volts per meter, so it's 12 volts divided by 7 millimeters. That's 1714 volts per meter. Maybe we'll need that later. Alright, well, let's see. It's a charge in there is positive charge. It's plus 42 microcoulombs. So, what plate does the plate move towards? It moves, well, if the electric force were the only thing in play, it would move up, but actually there's two forces, right? There's the electric force, which is directing it this way in the same direction as the electric field, and then there's the gravitational force here. And we have to take both into consideration. So which way is it moving? Let me calculate the electric force. That's QE. Okay, and that's 0.072 newtons. That's directed upwards. And the gravitational force has a magnitude of mg. So that's 0.025, because that's 25 grams. And that's 0.245 newtons directed downward. So since the force of gravity, the magnitude of the force of gravity is greater than the magnitude of the electric force, the charge moves down. It's not in free fall or anything. It's moving slower than free fall, but it is moving downward toward the positive plate. Okay, so there's the answer to part A. Now for part B, now that I got the dog to stop barking, I'm going to do part B. So how long does it take the charge to move down this distance? I guess in this case it's moving a distance of 3.5 millimeters, right? So 0.0035 meters. So we want to know how long that takes. And it's initially at rest. So if we could just find the acceleration, then we could find the time. And I think that's the easiest approach, is to use a forces argument. We could use work energy for this, and using work energy we could find the final velocity and so forth. Maybe I'll do it both ways. So let's see. If I do sum of all forces is equal to ma, that's, and I'll take the downward direction to be positive in this problem. That's the same as the direction of motion. So that would be plus mg minus QE, right? So for each force, I have the magnitude and direction. Magnitude, direction. And that's equal to ma. And of course, A is going to be positive because it's moving down. And down is positive. So I get 0.245 minus 0.072, 0.025A. Going up to here, that gives me an acceleration of 6.92 meters per second squared. And then I can solve delta y. I can solve this equation for time because I know delta y, I know v naught, and I know a. So 0.0035 meters is equal to 0 plus a half times 6.92 times t squared. Now just a quick remark on the 6.92. I said earlier that it's going to move down due to gravity because gravity overwhelms the electric force. But it's going to move slower than free fall, right? If it were in free fall, if there were no electric force in this problem, then the acceleration would be 9.8. So it's not too surprising that the acceleration is less than 9.8. It ought to be. Anyway, when I solve for time, I get 0.032 seconds. It doesn't take too long, but it doesn't have too far to travel. Now, if you wanted to use work energy for this, then we would say the sum of the works done by all the forces is equal to the work done by the electric force plus the work done by gravity is equal to the change in kinetic energy, right? Now, for both of these works, I can use F delta S cosine theta because the forces are constant and the acceleration is constant, everything's uniform. So I can use QE delta S. Now delta S here is downward. So in this case, it's cosine 180. The electric force does negative work in this problem. Let's see, that works out to be 0.000252 joules. And the work done by gravity is mg delta S cosine 0, since gravity and delta S are in the same direction, they're parallel to one another. Let's see, that works out to be 0.000858. I left off the negative sign here, sorry, the cosine 180 makes this negative. So if I add up those works, I get a net work done, or a total work done, of 0.000606 joules, and I'm going to set that equal to 1/2 mv squared. Of course, the initial kinetic energy, 1/2 mv naught squared, is 0 because it starts at rest, right? V naught is 0. Alright, so if I do that, I get V squared is equal to 0.0484, and then so that means V is 0.22. And so now if I know delta S and I know V naught and V, I can say that delta Y is equal to 1/2 V plus V naught T. And I can solve for time using that technique. And if I do that and solve for time, I get time of 0.032 seconds. So you're going to get the right answer either way, but I really think that the force method is more direct for this problem.